Yeah. Oh.
Millie, good morning. Thank you for joining this session. Thank you.
Hello, Mudathir. Mudathir, good morning.
Good morning, Millie. Thank you very much for joining. Thank you.
Yeah, I was testing my sound.
The same link. Thank you everyone for joining this morning session. I would like to welcome you all. So the webinar will start soon after 1 minute. So please, in the meantime, make yourself comfortable and ensure you have good internet connection, and also that your laptop has sufficient power. Also, during the webinar, type your question in the Q&A feature, which will be answered by the resource person. And also raise your hand to speak during the slot for questions and answers. Presentations, they will be available for everyone. Just 12 hours after this session, all the presentations and the recording will be available. The webinar also will be recorded, and you may follow also the webinar through YouTube live stream. If you click here, you can also follow the webinar. Can you remove that screen? Okay, good morning again. On behalf of the Executive Director of Nile Basin Initiative Secretariat, this webinar and this session, it is about the impact of climate change on stream flow and lakes and reservoir storage. The Nile Basin Initiative, in collaboration with the government of Uganda, is organizing a series of webinars in the 7th Nile Basin Development Forum under the theme, Deepening Nile Cooperation, Accelerating the Achievement of SDGs in Changing Climate. And the Science Policy Practice Dialogue is organized to bring together NBI with its stakeholders from Nile Basin countries and around the world. The goal of this 7th Nile Basin Development Forum is to enhance transformation processes in projects that will contribute to Nile Basin Initiative shared vision. And our vision is to achieve sustainable socioeconomic development through the equitable utilization of and benefit from the common Nile Basin water resources. There are many themes under this 7th Nile Basin Development Forum. And these themes, they cover different areas: adaptation to climate change, water resources management, basin investment plan, groundwater, water quality, transboundary water governance. The Nile Basin is one of the most critical transboundary water basins in Africa, with the River Nile playing a crucial role and resource for most of the economic and social activities for the countries in the Eastern and Northeastern Africa. The climate is changing, putting a range of natural and human systems at risk and promoting communities, governments, and organizations to step up their effort to adapt. That said, it is equally facing adverse effect of climate change, which is expected to worsen in future should little or no effort be done to avert the current trends. So welcome to this webinar, and let us have fruitful presentations and discussions, and let us work together to incorporate these findings in our decision-making River Basin agenda. Thank you very much. So allow me to remind you again, this morning's session, it will be about the impact of climate change on stream flow and lake and reservoir storage. We have with us here our panelists. We have Dr. Kinna. We have also Mr. Gizasho Kasa. We have Mr. Waswa Peter, and we have Ethiopia Bisrat. Those are our panelists. And the title for Dr. Kinna for this session, it will be about modeling the impact of the changing climate on stream flow in the Desa catchment Abai Basin in Ethiopia. And the title for Mr. Gizasho is about climate change and its impact on stream flow in the Upper Blue Nile River Basin. And the title for Mr. Waswa Peter is about analysis of projected wet and dry events and their impact on the hydrology of Ugandan lakes. And then we have Bisrat Zaleke, and her title is about evaluation of global climate indices and their ability to predict the relatively variability of seasonal precipitation magnitude, the case of Ethiopia. After this presentations, we will have like a kind of panel discussion. And also, we will answer your questions. If there are any questions from the participants, we will answer them also. So allow me please now to invite Dr. Kinna Tadesse to share his presentation. And the floor is yours, Dr. Kinna. You can put it in a slideshow mode. Okay. Yes. Thank you. Please kindly introduce yourself again And the floor is yours.
So is my sound okay? Can you hear me?
Yes, loud and clear.
Yeah.
Thank you. Go ahead.
Thank you. Thank you very much. I'm privileged to be the presenter here. Thank you for the invitation. My name is Taddasa Tujuba Kana. Of course, the Ethiopian name is a bit different from the others. As a surname, we don't have surname. My grandfather is Kana. So I'm working at Arba Minch University in southern Ethiopia in the Water Technology Institute, the department called Meteorology and Hydrology. My research focus mainly in the climate, but I usually relate it to water resources. And I also teach courses related to these focuses. So my presentation title is Modeling the Impacts of the Changing Climates on Stream Flow in the Desa catchments, Abai Basin, Ethiopia, one of the catchment contributing to the Blue Nile River Basin. So as introduction, I have issues related to climate change, water availability, and so on. Obviously, water availability is affected by climate, both variability and change, in addition to other environmental factors. So sometimes in some years, about half of the global population is in a scarce of water. And the reason could be either climatic or non-climatic. And even it's expected to be more worse because of the changing climate. So the IPCC put forward that even even if we are able to cut the emission today, the impact will still persist for some time in future. So it's important to deal with the impact of climate change in different socio-economic sectors, and my focus is very narrowly on stream flow. So the catchment we are dealing with, the Desa catchment, is the second largest in terms of area, sub-basin of the Abai Basin, and it also significantly contributes to the flow. About 11% flow contribution is from the Desa sub-basin. So in that case, understanding the dynamics of water availability is so important under the context of climate change and actually other environmental factors. So the main aim of this study is to analyze climatic elements, climatic factors, and relate it to stream flow. So the Desa catchment, as you may see here, is part of the Abai Basin. It's in the southwest part of the Abai Basin, and is characterized by heterogeneous elevation from 852 to 3041 meter above mean sea level. And the temperature also varies. The maximum temperature varies from 21 degrees centigrade to 30, and the minimum temperature from 10 to 20. So it's if you see the rainfall again, it's characterized by high spatio-temporal characteristics. So the main rainy season is the summer, but this area receives about 10 months in a year, rainfall 10 months in a year. So we collected data from different organizations, meteorological data from the Ethiopian Meteorology Institute, flow data from Ministry of Water and Energy of Ethiopia, output of the regional climate model from the Cordex Africa domain, has been actually a popular a source for Africa, at least in the CMIP 5. And we have evaluated the models with observation, and based on the evaluation, then we did the bias correction. So this is actually, I'm not sure whether my arrow is working, but the right figure, the line plot,
It's
is
working.
showing.
Thank you.
It's working. Okay. In that case, yeah, this part is the evaluation part, at least on the mean climate condition. So these are the three regional climate model outputs we found very related to our observation. And their ensemble actually is even better than the individual models. Then based on that, we calculated evapotranspiration using Hargreaves. And then we did the trend analysis using the modified Mankindal trend test. And we analyzed actually the variability and trend in the historical and future periods. Then what we did is to see the impact using the impact model. We used here the swapped hydrological model. So the results, the historical period, so it's found that there is a slight increase in trend of rainfall, which seems, yeah, it's okay actually. It's actually related to, it could be related to the surface temperature cooling recently happening, which has been causing dry incident in the south part of the country, but in the northwest part, we see the slight increase in rainfall amount, the slight increase in trend, and a decreasing trend of temperature, both minimum and maximum temperature is observed during a historical period. So in the same manner, so we did projection for three classified future periods, 2021 to 2040, 2041 to 2060, 2070, 2071 to the end of the century. So in that analysis, it's found that the trend in rainfall doesn't show consistent pattern. However, the temperature, as far as temperature is concerned, both in minimum and maximum temperature, it's found that there is an increasing trend in temperature in all three future periods we considered. And in actually, we considered, I should have actually explained more. I don't have such enough time. We considered two scenarios, RCP 4.5 and 8.5. So an increasing trend in temperature in both RCP 4.5 and RCP 8.5, and all three future periods were found. So with this, there is expectation actually that with increasing temperature, we expect increasing in evapotranspiration, and that will result in a decreasing stream flow, general expectation. So in terms of pattern, we could not find distinct pattern in future or in projected rainfall. But in terms of evapotranspiration, the change in evapotranspiration is mostly positive. That means there is an increase in future evapotranspiration, and unless the same pattern in rainfall is observed, actually, we can expect that there will be a decrease in stream flow, as ultimate source of stream flow is rainfall. So we use the SWOT hydrological model. We calibrated and validated it and used for impact assessment. So in that case, we found change in stream flow is positive for dry months. Dry months are actually based on the description I gave in the introduction part. Changes in stream flow is negative for wet months, for especially June, July, August, September. These months are the main rainy season in the area. So it's not good. In terms of season, changes in stream flow is positive for spring season, and it's negative for summer season. But it looks, when we consider annual, if we see only annual, it may lead us to the wrong conclusion that the stream flow is increasing in the area, but season-wise, the main rainy season is decreasing, which needs actually attention in water resource exploitation in the area. So as a recommendation, I put 2 or 3 points. Water resource availability should be included in any planning, and the resource should be used wisely, could be general. And in that water resource availability assessments, the impact of climate change should be considered, in addition to other environmental or whatever factors affecting the water resource availability. Any activity related to soil water conservation is recommended to cope up with the expected decrease of stream flow. So there is a projected decrease, especially in the main rainy season. In that case, water conservation in any form is recommended. Thank you very much. I have done.
Thank you. Thank you very much, Dr. Kinna. Thank you for the excellent presentation about modeling the impact of the changing climate on stream flow in the Dessa catchment Abai Basin in Ethiopia. And you used a different data set in this study. You also used the Cordex, this downscale data set, and you bias corrected. You have done good work in evapotranspiration and in the calculation in order to use it in the impact model. And SWOT model, it was used, and 2 scenarios, RCP 4.5 and business as usual scenario, RCP 8.5, which is like the extreme scenario. It was also used. You did like a good analysis for Q during like the dry season and also the rainy season. And from your study, you found that Q is negative for the rainy season. But thank you very much, Dr. Kinna, for this excellent presentation. Now you can unshare your presentation, please. Thank you for stop sharing. Now I will go to Mr. Gizacho Casa, and his presentation is about climate change and its impact on stream flow in the upper Blue Nile Basin. Please share your presentation. Introduce yourself first, and the floor is yours.
Thank you very much. Waiting, sir.
Yeah. Thank you, Mr. Gizacho. Please share your presentation.
Okay, Minister.
Okay. Yes, thank you. You can put it in a slideshow mode. Maybe you start from the first slide.
Yeah, we can start.
Okay. Please introduce yourself first,
Okay.
and the floor
Thank
is
you.
yours.
I'm Zacho Kasa from Arvamich University, again, in meteorology and hydrology faculty.
Maybe turn off your video. So hopefully we will have good streaming. Turn off your video and do your best to increase your voice, please.
Okay. Can you hear me?
Yeah,
Yes.
introduce yourself.
Yeah, I'm Zacho from Arvamich University, again, in meteorology and hydrology faculty. I have a basic degree in meteorology science and climate change, Master's of Science. This is work in my master's thesis since 2016 in the Upper Blue Nile Basin. I have been trying to assess the impact of climate change on stream flow by setting hydrological modeling like HMS on 3 large basins. So here is an introduction or the rationale of the work. As we know, climate change can cause significant effect on water source, how by resulting change in hydrological cycle. How it affects both significant change in mean annual precipitation and average temperatures through various periods are principal implications of climate change. These are the first manifestation of climate change, which are considered that the main determinants of the hydrological cycle, seasonal occurrence, and loss of water in rivers and wetlands and soils in the basin. So the use of TCMS outputs and hydrological modeling is a best method in estimating future possible stream flow change due to climate change. So different climate model ensembles results are effective in reducing uncertainty, which means I've used 3 five models, ensemble mean, and the 4.5 and 8.5 scenario for long-term climate simulation using the hydrological model. As a background, here is a steady area description. This is from those 12 basins of Ethiopia. This is Blue Nile Basin, the Upper Blue Nile Basin. From this, the hydrological model has been calibrated and validated into large sub-basins. This is the Abai Kasi from the Tana sub-basin, and the main Balas, and this is the upper catchment, the Disa. So I have used the HMS hydrological modeling by calibrating and validating by the actual site-specific hydrometeorological data. Here are the data sources. It is Ethiopian Meteorological Institute for historical observed data. And the other SIM5, the same climate data by using SIM5, the Earth System Grid Federation. And then we have used Earth Explorer, which is in the land cover, soil data for the HMS model inputs. This during the model from those 3, I have tried to show the catchment. These are the observed, the RCP grid points. Have been using it, and meteorological stations. This is the hydrology. This is the dam to show the physical watershed map. This is HMS, the basin model, hydrological modeling basin model, physical watershed map for Kase. For the other also computed. Results and discussion due to limitation of slide. I'm presenting some specific results. There is a Mankendal trend test to assess the climate change Based on the statistics, there is no significant and consistent trend in the basin based on three basins. So the work concludes there is a summer rainfall enhancement, but there is no constant increase in significant trend. Here is a hydrological modeling, HHMS calibration validation, the results, and the performance, which has been checked by different objective functions. The model performs in a good manner, as shown the results. Again, the results have been tried to compare in different time slices of future, 2050 and 18, into scenarios. This is the ensemble in different sub-basins, Sarkase and Didesa, Balas, were just to compare the peak flow and runoff depths, to consider evaluating mean annual flow volume relative to historical. The comparison, so we have a conclusion later. This is the predicted stream flow using the ensemble mean of the GCMs as predicted. Based on the prediction, there is a change analysis here. So seasonal stream flow change. Precipitation, this is the precipitation and the stream flow change, which is consistent or symmetry with the precipitation change. So this to confirm that sensitivity with precipitation. So the result concludes based on this precipitation change and stream flow change. There is an enhancement of precipitation in the wet season, that's June to September 1st. And again, the accompanied stream flow also increase or enhance it relative to the historical record. All three model ensemble predicts that the stream flow enhanced in three sub-basins during the wet season relative to historical. This is the Kase basin, this is a stream flow, especially the August and July stream flow is, or the runoff generated based on the GCM results are very enhanced due to climate change. As a conclusion, the future rainy season due to August precipitation and accompanied runoff becomes highly augmented or increased. Ensemble means of multiple GCMs and derivations of high resolution simulation could improve climate change uncertainty and runoff prediction in the basin. Future wet season flood forecasting and precautions should be in the flood plain area of the Nile basin should be consolidated or should be enhanced relative to historical. Thank you very much. I'll finish my presentation.
Thank you. Thank you very much, Mr. Gizaccio, for this excellent presentation. The title of Mr. Gizaccio, it was about climate change and its impact on stream flow in the upper Blue Nile River Basin. He used 3 GCMs. He used 2 scenarios, RCP 4.5 and RCP 8.5. And just for our participants, RCP is, this is the representative concentration pathway. There is RCP 2.6, RCP 4.5, RCP 6, and RCP 8.5. And RCP 4.5 and 8.5, they are widely used. And our speaker here, he used these widely used scenarios, RCP 4.5 and RCP 8.5. RCP 2.6, this is the conservative scenario. RCP 8.5, this is business as usual scenario, or this is like the worst scenario. And he used also different data sources. And he used in his analysis this Mankimball trend test. And also he used the HHMS And he looked at two projected time in the future. He looked at 2050 and 2080. And one of the important results, he found that the stream flow, it was enhanced in these three areas due to climate change. Maybe for the previous speaker, he found that it will decrease. But of course, there is a high spatial variability. Sometimes you may find the rainfall or the stream flow, it increases in this part, but it is decreasing in the other part. So there is no any kind of contradiction here. And also at the same time, different models are used. We know that these GCMs, they produce different results. So that's why it is good always to use as much as possible in this number of GCMs in your study. So there is no any contradiction between the second and the first presentation. And allow me again to thank Mr. Gizaccio for this excellent presentation. And also for our panelists, please remain. You will receive some questions by the end of these presentations. And also there is a panel discussion. Now I will go to the next speaker, Mr. Waswa Peter. And his title is about analysis of projected wet and dry events and their impact on the hydrology of Ugandan lakes. Yes. Please introduce yourself well before you start your presentation. The floor is yours, Mr. Waswa. Thank you.
Hello, everyone. All protocol observed. I'm Peter Waswa, having a background in meteorology from Makerere University. And also currently I've just finished my master's in hydrology from Lord's University in South Africa. Currently I'm at the headquarters of WMO doing my internship in Geneva. Welcome to my presentation with the title, An Analysis of Projected Wet and Dry Events and their impact on the hydrology of Ugandan lakes. As we know, all of us, that lakes provide a lot of services to the millions of people that surround them. And on top of that, they provide ecosystem functionality. However, what to worry is that recent variations in their hydrological characteristics are posing significant concerns on societies, economies, and ecosystem functionality. And the recent results are also indicating that surface water viability in most of these lakes is expected to vary considerably. And this trend is likely to continue in the future and also projected to affect various human activities and ecosystem functionalities. In Uganda, of course, there seem to be some little or insignificant information about the expected impacts of climate change on hydrology of lakes. And thus, the most aim of this study is really to provide some information about the expected impacts of climate change on hydrology by applying an integrated approach to analyze the impacts of projected wet and dry events on the hydrology of Ugandan lakes. On your right, you can see a figure. Most of you have ever seen this during, I think, 2020. This figure was taken by New Vision near Katabi. This is where the lake levels were extremely high, and you can see what was happening there. So, my study basically focused on the 4 Ugandan major lakes, and this is Lake Victoria, where the NBI actually is having the secretariat. We have the Lake Albert, Lake Choga, and Lake Edward. The data sets we are involved satellite rainfall data, the CHIPS, which is the climate hazard group infrared precipitation with station, and this data was used to bias collect the codex data. Of course, also for the future, because I'm looking at the projections, I had to use the codex, which is the coordinated regional downscaling experiment for the period of 2023 to 2040 under two representative concentration pathways, as earlier on been explained by Dr. Modefel. Then also I used satellite water level data, which was obtained from Global Water Monitor, and it has a span from 1993 to 2022 for Lake Victoria and Chog. However, Albert and George, their data set spanned from 2016 to 2022. The analysis involved using standardized anomaly index, which was used to generate the wet and dry events from the codex data, and this was basically done using the Python environment. And then for the projected water levels, ALA-based ALIMA model was used to generate the future water levels using the historical water level data sets. And what we are finding from here, when we look at the projected water levels over Lake Victoria, we expect to have some increase in the water levels, particularly in 2025, 2026, and SATA1 under LCP 4.5, whereas under LCP 8.5, we expect to have increase in water levels around 2030, SATA3, and SATA4. We expect also to have a decrease in water levels, major around 20, SATA1, SATA5, and SATA9, and this is more especially under LCP 8.5. When you look at what will happen to the projected water levels along Lake Chog, we see that we shall expect an increase in the water levels around 2031, 32, and 36 under LCP 4.5. For LCP 8.5, we only expect to see increase in the water levels around 2033 and 34. The decrease, or which are the dry events, are expected to happen in 2030 and 39, which is under LCP 4.5. For 8.5, we expect to have a decrease in water levels around 2026 and 2031. When you look at what will happen to the projected water levels in Lake Albert, we see an increase which is expected to be around 2023, 2028, and 2032 under LCP 4.5. And for LCP 8.5, we expect to see an increase around 2024, 2029, and 2034, and probably 2036. However, we shall also experience some decrease in water levels, that's around 2026, 2030, 38 for LCP 4.5. And for LCP 8.5, the decrease in water levels in Lake Albert are expected to be in 2028, 31, 32, 38, and 39. For Lake Edward, we expect to have wet events, which will definitely trigger the water levels to rise up. And for your information, the water levels we are looking at, the water levels which are in above the mean sea level, and we expect these to increase around 2023, 2032 under LCP 4.5. And under LCP 8.5, the increase will be in 2025 and 34, whereas the decrease is expected around 2029, 2030, and 2034 under LCP 4.5, while LCP 8.5, we expect a decrease in the water levels around Lake Edward around 2031 and 2038. So what are we concluding from these results? We are seeing a significant increase in water levels, which are majorly the expected events, and this particularly will be observed along Lake Edward, Choga, and Victoria. However, Under LRCP 8.5, we expect Lake Edward and Victoria to have significant decrease in water levels. And we have to make a general conclusion from this study that over these 4 lakes that were considered, we expect to have a general decrease in water levels under LRCP 8.5 as compared to LRCP 4.5. And here to notice that although in this study rainfall was the only variable that was considered, it probably reflected some good results as far as water levels were concerned. And nevertheless, other parameters should be considered in conjunction with rainfall, like the temperatures. What we recommend from this study is that we are encouraging the Nile Basin and other organizations to increase the number of hydrological monitoring stations within the Lake Basin so as to complement and validate the satellite-based data. As you saw, this study basically relied on satellite-based data. We encourage also the real-time early warning system to be developed and initiated to all lake basins within the Nile Basin and other regions. And lastly, we discourage deforestation and encourage afforestation and reforestation within the lake basin. And this, we hope that it will increase the microclimate effect, which will definitely reduce the uncertainties that will be associated with increasing water levels and also decreasing water levels. Thank you for listening to me.
Thank you. Thank you very much, Mr. Waswa, for this excellent presentation. The presentation, it was about analysis of projected wet and dry events and their impact on the hydrology of Uganda lakes. You used the integrated approach to analyze the impacts. And here you focused on these 4 large lakes, Lake Victoria, Lake Tioga, Lake Albert, and also Lake Edward. You used the CHIRPS dataset for bias correction and CHIRPS dataset. This is one of the good datasets, and it has also different resolutions, 0.05, 0.5, and it is widely used also here in the region. You use it to bias correct the RCPs of 4.5 and 8.5. And of course, we cannot use these GCMs without bias correction. For any impact study, if we want to use these GCMs as an input to our hydrological or agricultural model, we need to bias correct them. And you did that very well. And also, you used for the impact here, you used also Python, and you used good tools in this study. And you did an analysis for different periods, different projected periods in the future for these 4 lakes, at which year we may project like an increase on the water levels, and also on which year we may project like maybe relatively low water levels. And also you gave like some good recommendations of using like more hydrological stations. And currently we have a project, a hydromet project, and it was somehow now reaching a very good stage. We have more than 60 stations over the Nile Basin, which provide real-time information for the countries. And also you encourage using early warning systems. We have the Nile Basin river flow forecasting system. We are now in the process of refining that system. And hopefully 1 year from now, we can have a good early warning system, which can give also forecasted water levels also. Thank you. Thank you again, Mr. Waswa, for this excellent presentation. Please stay with us. And now we will go to the next presenter. Miss Ethiopia Besrat Zelleke. And her title is about evaluation of global climate indices and their ability to predict the relatively variability of seasonal precipitation magnitude, the case study of Ethiopia. Yes, I can see you are sharing now your PPT. Please first introduce yourself well, and the floor is yours. Thank you.
Okay, thank you, Modatir. So thank you for the introduction. My name is Ethiopia Bisrat Zelleke, and I'll be presenting on exploring the potential of global climate indices and predicting seasonal rainfall variability in regions of Ethiopia. I'm a doctoral candidate at Florida International University, and I work primarily on modeling drought propagation and analyzing sectoral and system-specific droughts, trying to specifically understand the cascading effects of meteorological, hydrological, and agricultural droughts, and trying to integrate multiple models so that we can do intervention approaches at the end. My study area mostly focuses on river basins of Ethiopia, and this study is part of my research, which focuses on predicting precipitation by using global climate indices as well as local land characteristics. So I'm going to start by briefly talking about the motivation of this study and talking about rainfall variability and prediction in the context of different regions, and in particular in Ethiopia. So rainfall variability in most regions of the world is largely shaped by large-scale climate drivers. These climate drivers often occur within ocean basins. They can be in the Pacific Ocean, in the Atlantic, or in the Indian Ocean, and they can also occur as short-scale atmospheric circulations, which affect precipitation patterns due to teleconnections. In addition to these large-scale climate drivers, we also have local land feedback that either amplifies or dampens the effect of these large-scale climate drivers, which often makes it difficult to make accurate predictions for precipitation. So not being able to make accurate predictions in precipitation indirectly means that we're not really going to be able to predict droughts and associated floods. So in addition to these local land feedbacks that alters global climate drivers, we also have variable skill of these large-scale climate drivers themselves, which means that in specific regions of the world or in specific regions of a single country, we could have varying skills of these global climate predictors, so we may not necessarily use the same global climate predictors in different parts of the country. This highlights the need for localized models, which in the sense of converting information across spatial scales is important, particularly looking at hydrologic and agricultural studies. So one of the main challenges associated with using predicted precipitation is that it comes at a very coarse spatial scale. These coarse spatial scales may not necessarily take into account localized feedbacks, which often makes it difficult to use them in localized hydrologic studies or watershed studies, as well as agricultural studies, or essentially trying to integrate these three different types of models. So what we did is, in this study, we analyzed how precipitation patterns vary in Ethiopia and how local land feedback would affect those precipitation variabilities. So looking at the main challenges that occur in Ethiopia, as my research essentially focuses on droughts, I'm more interested in analyzing these dry season flows or dry precipitation patterns. So in Ethiopia, over the past couple of decades, we've seen significant major droughts, notably in the 1984, 1983 and 84, 2002, 2009, 2015, 2022, which was some of the recent drought periods in Ethiopia. So the main challenge associated with droughts is that we lack societal resilience because of that high reliance on rain-fed agriculture and rainfall. So oftentimes, instead of having a proactive approach through prediction methods, we usually have reactive approaches to drought management through food assistance or some sort of drought relief. This is mainly because Pacific, as well as just above Australia. I also looked at the Indian Ocean dipole, which occurs over the Indian Ocean basin, and I looked at the Madden-Julian oscillation, which is an atmospheric circulation pattern that occurs at a relatively smaller temporal scale. So in combination with a regionalization map that was adopted from a study done by Berletta Brahanu, we combined these global climate indices and joined that with the regionalization map that was produced by Berletta Brahanu. And then we developed a machine learning algorithm or a machine learning model, specifically a random forest classification model, which is an ensemble decision tree machine learning model. So we combined these 5 global climate indices, associated them with the regionalization map done by Berletta Brahanu. And this regionalization map essentially looks at variability of precipitation. That means timing of precipitation, magnitude, as well as duration of precipitation in different parts of Ethiopia. So it essentially divides the country into about 15 rainfall regimes, in which each rainfall regime has a distinct weather pattern. So by combining the global climate indices, which are our predictors, and precipitation that was obtained from chirps into each of these regionalized weather climate regimes, we developed a classification model that would forecast seasonal rainfall. This seasonal rainfall was done for both summer and spring season. So in the summer season, which is essentially July, August, and September, and spring was March, April, and May. And what the model does is it distinguishes between dry, normal, or wet seasons. After we were able to develop this model, we looked at the model performance. So the first thing that we looked at was the ability of the model to predict summer and spring rainfall, as well as the robustness of the model in predicting dry, normal, or wet seasons. And these were some of the evaluation matrices that we used. And then finally, and most importantly, we ranked the predictors based on the importance to each region, which is the premise or motivation of this study, which states that the skill of global climate indices is dependent on spatial location. So we wanted to account for that spatial dependence. So looking at the results, the first result I'm showing here shows the precision, recall, and F1 score of that classification algorithm that we developed. So we obtained very good results, ranging from about 0.76 to 0.93 in different regions of Ethiopia. And we see that for both summer season as well as spring season, we have a good performance in our classification model. Further looking at the robustness of the model, in analyzing dry season, normal season, and wet season precipitations, we see that the model performs relatively well in terms of classifying dry season rainfall, followed by wet season and normal season, all of which have a very good receiver operating characteristics curve. The last result that I'm going to show is the spatial variability of these predictors and their relative importance. So the map that I'm showing here, so at the center, we see these 15 rainfall regimes divided by color. And then around those, we see these bar charts that show the relative importance of these 5 global climate indices used to classify seasonal precipitation. So the location of these bar charts are essentially the location of where these rainfall regimes are. So in most parts of the country, we have the Indian Ocean dipole, which is the most important global climate index in terms of explaining precipitation variability for summer season. particularly in the southern, southwestern, and southeastern parts, we see the effects of the Indian Ocean dipole mode being the largest in terms of explaining that precipitation variability, whereas in the northwestern part of Ethiopia, the Madden-Julian Oscillation, and also in the northeastern part of Ethiopia, the Madden-Julian Oscillation has a most significant importance in terms of predicting or explaining that rainfall variability. Other regions, such as northern Ethiopia, are dominated by the Nino 3.4 sea surface temperature region, as well as the eastern part of Ethiopia, which is dominated by the Southern Oscillation Index. In addition to this, we also looked at season precipitation patterns, and we saw that the skill of these predictors flipped or changed when it came to that spring season, and the spatial association reduced. So in much of these basins, we have variable global climate indices that are able to predict seasonal precipitation, where in the southern and southeastern, the Indian Ocean dipole, which explains a large proportion of precipitation variability, whereas in the other basins, it's actually mixed between the other four global climate predictors. So this shows that whenever we want to study these precipitation variabilities, especially on a seasonal scale, it would be important to select these global climate indices that is associated with different regions of Ethiopia. So in terms of applying these results in the context of the Nile Basin, I propose 3 different recommendations. The first one has to do with water resources management. So this research demonstrates the effectiveness of a random forest classification algorithm, which is a machine learning algorithm, and that is completely data-driven, using global climate indices and precipitation, and essentially looks at predicting rainfall variability on a seasonal timescale. So by implementing this model in the Nile Basin region, decision makers can proactively manage water resources, reduce the impacts of droughts, and optimize water allocation for various uses. And this includes agriculture as well as drinking water supply. Another important application is to tailor climate resilience strategies for different Nile tributaries. So this research identified variations in significance of climate indices for different rainfall regimes in Ethiopia, which is a significant tributary to the Nile Basin. And tailoring climate resilience strategies to each specific region could lead more to an effective preparedness and response measure by taking into account the unique climate challenges that is faced by each section or each tributary. And then finally, in terms of fostering collaboration, so regional cooperation in climate modeling can potentially lead to more comprehensive and accurate data collection, which is essentially required for building any type of machine learning model, because is mainly the amount of data used as well as the quality of the data. So by sharing data and resources, Nile Basin countries can collectively improve their ability to predict and also respond to climate-related challenges, and this can in turn foster greater cooperation and resilience in the face of climate change in the future. Can be used to enhance water resources management, to adapt to climate variability, as well as deepen cooperation among Nile Basin countries.
Thank you. Thank you very much, Ethiopia, Bisrat Zalleke, for this excellent and outstanding presentation. The presentation, it was about evaluation of global climate indices and their ability to predict the relatively variability of seasonal precipitation magnitude. And here you looked at the teleconnections. And the good thing about teleconnections, they give good signals for Ethiopia. And here you looked at the sea surface temperatures in different places, like the area in the Pacific Ocean. When it warms, the area which we call it Nino 3.4, and this area it is between 5 north and 5 south, 120 to 170. That area is very sensitive to the climate of Ethiopia. You looked at different sensitive areas. This Nino 3.4 area in the Pacific Ocean, and this it connect also to the El Nino and La Nina. El Nino, this is the warming. La Nina, this is the cooling. El Nino is connected with drought. La Nina connected with floods. You looked at the mid-Julian oscillation and the Southern Oscillation Index also, and the IOD, the Indian Ocean dipole, the positive Indian Ocean dipole, and also the negative Indian Ocean dipole. You looked at the east and the west of this Indian Ocean dipole, and those are sensitive areas, and they modulate the climate around the world, and they are directly connected to the climate and to the rainfall of Ethiopia. So you used very well these teleconnections in this as like a large scale drivers. You mentioned clearly that the coarse scale sometimes it may not give good messages, and also the challenge of Ethiopia related to the drought. And you mentioned different periods of drought in Ethiopia. And also you went through these large scale features and these 5 indices, and how you used this state-of-art technique, the machine learning, on your analysis, and also how to combine those predictors and to develop classification model for 3 periods dry, normal, and wet. And you looked also at the model performance, and also on how good this seasonal rainfall prediction, and how is it somehow related to this spatial variability of the predictors. And also, as I said, the skill of the prediction, and you gave nice recommendations on how to enhance the water resources, and how to tailor this climate resilience, and how to promote the regional collaboration. Thank you again, Ms. Ethiopia, for this excellent and outstanding presentation. Maybe now we can go to our Q&A session. I have some questions here for our panelists and for our speakers here. Okay, there is the first question: why the evapotranspiration is expected to increase during the wet season if the temperature is expected to decrease, as well as the precipitation in the same period? So this is the first question. So maybe we can answer one by one. So I think the first presenter, Dr. Kinna, was this question for you?
Actually, I've tried to type it, and the increase in the expected, I put the expected increase in evapotranspiration is during projected future period, is not for the historical. So while actually the rainfall is increasing and the temperature decreasing in the historical period, I don't expect an increase in evapotranspiration. The question is right, but the period that I put the expected evapotranspiration is increasing is for projected future periods. I can shortly answer like that.
Okay, I can see there are many questions for you. There is another question. Do you have EP data? If not, how we can be sure about its increment and decrement without calibrating and validating the SWOT model with the EP data? I think this question is also for you.
The ET data, actually during again historical period, is computed from temperature, maximum and minimum temperature. We used the Hargreaves method, which uses actually maximum and minimum temperature. So in the similar way for future period, without going into any modeling, the ET is calculated from model output products, climate model output products. That is actually evaluated and bias corrected, and it's directly computed, not from the SWOT. So we give the ET to the SWOTs to simulate the stream flow. I think I'm not sure whether the the question is answered, but it's like that. The ET is computed before running any hydrological model, or without running SWOT model in this case.
Very good. There is also, bear with us, there are many questions. There is one also, he said, I can see that from Dr. Khalid Hasaballah from ECPAC. He said, I can see that one of the major results is the decrease in the stream flow during, I think, the main rainy season. And I was wondering if there is a similar study for neighboring catchment to compare the stream flow results.
Okay, yeah, that is a very nice question, impressive question, which I should look into it in detail. But most of the studies I looked focuses on annual values, impact of climate change on annual stream flow, and so on, so on. So what I give as a hypothesis is, this climate change impact may have opposite signal on different seasons. Say, for example, decreasing the main rainy season, increasing the maybe the other rainy season. And if we consider the cumulative, the signal may be smoothed. In that case, it's important to treat seasons independently. So I have to see in detail again about maybe the very recent studies, whether they have considered seasons separately in different catchments of especially the Abai Basin. Yeah, it's a very good question.
Thank you. Thank you. There is a question. It is for you, but I think I will make it common. You already answered many questions. The question said, as there are many climate models, can you please explain the reason of selecting these 4 models? And here, I will make the question, the reason for selecting these models for your case study. So you can quickly, just in 30 minutes, answer this one. How did you select the models for this study?
Maybe I can go first.
Yes, you can go first, Waswa.
Yeah, sometimes it depends on the literature which is available, and you can see in East African region, most of the scientific researchers have really used different kind of models, and they have made some good recommendations. So then it's from there, then you get the idea that, yeah, this kind of model is best in this region compared to other regions.
Yes. Mr. Gizaccio and Dr. Kinna, would you like to add anything?
I agree with Waswa. That is the thing we do in order to actually minimize the computational expense. We usually go to literature. I did the same, and see models that work in a larger region, East Africa, for our case. And then we do not directly use it. We evaluate it with our observation and use it. Actually, there are studies actually starting from the whole or many models and minimize to certain models. So I agree with Waswa. That is a good answer for me.
Thank you. Would you like to add anything? Is that sure? That is okay.
Of course, I agree with those replies, but mostly the best way is, using multi-models and check their performance. And the best performing model may use for our impact model like Hydroska model or agricultural. The performance should be checked very well in different methods.
Yes, thank you.
Of course.
Very good. So maybe also I can add here, like if the model historically capture well the seasonality, we assume also in the projected period, it will also perform well. If it also capture like the extremes, we assume also in the projected periods, it will do the same. We look also at the consensus of the models. You find sometimes many models, historically, they agree on the same message. So here, this is what we call it the consensus of the model. If it is close and have that kind of consensus, it is also like a good model. And the skill historically also, and in capturing the natural variability in the past, this also, it means that this model will be like hopefully a good model for projecting that specific catchment. And also here there is high spatial variability. The model who give maybe a good result in the equatorial region, it may not give a good result in the upper catchment of Ethiopia and vice versa. The other thing also, we need to refrain from using only one model. And I can see all our like speakers, they didn't use one model because it could be like a wet model or a dry model or a hot or cold. So it is always recommended to use a number of models. And even if you can even use like the whole set of ensembles, it is even better to use the whole set of ensembles and then come with the conclusion or with the message from those models. There is also another question here to Mr. Waswa. The projected increase in water levels in the major lakes flowing downstream would have adverse effects, including flooding in South Sudan and Sudan. So what measures have MBI ahead of time to remedy the effects? So you can attempt, but I can answer also this question.
Yeah, I think I answered this question, and I was just, because he's asking what NBI can do ahead. So my answer was maybe to to encourage NBI to include to do more on early warning systems, and also to design, if possible, prospect hazard maps and disseminate them to the relevant stakeholders to alert the community of what is likely to happen in time. So all this is at the table of NBI. They are the one responsible for this, what will happen to downstream, because these water levels seem to be will increase in the future and causing havoc in the downstream areas. So it is the role of NBI. Mine was just to provide information.
Thank you. Thank you very much. Also, I can add that we have a basin monitoring bulletin. This is a quarterly basin monitoring bulletin. We looked at the large lakes over the Nile Basin. We look at Lake Victoria, Lake Joga, Lake Tana, and Lake Nasser. we monitor the water levels on those lakes. And of course, the good thing here, Lake Tioga specifically, it acts like a natural early warning system for South Sudan and Sudan, because when the water level, for example, in 2020, when it increased by 2.2 meters, like around May and June, it was a clear message that large floods will come soon to South Sudan and Sudan. And we wrote an article at that time at the NBI website about this, like expected floods in South Sudan and Sudan. Also, our Nile-based river flow forecasting system, the one that we are trying to refine now, it gives also the projected water levels over these large lakes also. So this is what we are doing at NBI. There is another question here. He said, or she said, I was wondering if you, sorry, there is like some, yeah, if there is any correlation between the considered climate indices, which would influence the interability of the final result. Did you check that? I think this is for you, Ethiopia. I don't know if you get the question. If you want to read it. Also.
Yes, I guess.
Okay.
Yes, I've read the question. It's a very good question, and well, the model that we used is random forest, and one of the disadvantages of a random forest model is that it doesn't necessarily give us the parameters or the correlation of each index with that of the predicand or with that of the precipitation. However, it does give us the relative variability or the relative skill of these predictors, which was what we were looking for. But I also did this same model using a logistic regression model because I was interested in the question that you asked, and I wanted to know how each of these indices correlated with precipitation. And that that logistic regression model showed me that there was a negative correlation between summer rainfall for Indian Ocean dipole and Madden-Julian oscillation, whereas it was a positive correlation with East Indian Ocean dipole and the Nino 3.4 SSD. The Southern Oscillation Index didn't really have that big of a parameter value. It had about 0.086 compared to the other ones. It was quite small. So these four indices had more of a larger correlation, where the negative correlations were the Indian Ocean dipole west and Madden-Julian oscillation, while the positive correlation was the Indian Ocean east and the Nino 3.4. We did the same thing for the March, April, May rainfall as well, and these variables are almost similar. So yeah, that's a great question. Thanks.
Thank you very much, Ms. Ethiopia. There is another question. No, I think I read all the questions. My colleague here, he's printing. He said there is one more question, but we can take it maybe later. Thank you very much, our panelists, for answering very well all the questions of our participants. Maybe now there is one question. You can still answer it in the chat area, but we can go now to the panel discussion. There are like two questions. Maybe I assume you may take like 1 minute, maximum 2 minutes. Yeah, like there is no need for like long elaboration of like 5 minutes or more. Just maybe maximum 2 minutes is enough. Even if you can take less, still that is fine. So the first question for our panelists, how will stream flow in small and large basins be affected by climate change? If you can give like some answers for this question, I can start with Dr. Kenna. Do you like to start, Dr. Kenna, or yeah?
Well, you can give it to someone else if say
Okay.
Waswa or
Okay,
anyone else.
so maybe Waswa, Mr. Gizacho, or Miss Ethiopia. The first question, it is about how will stream flow in small and large basins be affected by climate change?
Can I go first?
Yes, go ahead.
Yeah, so what is happening is that we have seen from all the presentation and from what IPC reports are saying that rainfall is either increasing or decreasing, and therefore we don't have a consensus of wet and drier. But what we are seeing increase in temperatures, and what will happen to the stream flows is that we expecting to have a variability in stream flow, both high and low, depending on the variability in the rainfall. That's what I can say.
Thank you very much for this excellent response. And it is true, all the models, they agree on the increase of the temperature, but the uncertainty related to the projected rainfall, which is directly connected to the projected flows, there is a level of uncertainty related to the rainfall, which is directly linked to the flows. But also on the same time, we are looking at different temporal periods. And also we look at somehow there is that spatial variability. So if we look at 2030, it is different from when we look at 2050 or 2080. And the same thing when we look at, for example, the upper catchment of the Blue Nile, or when we look at Ethiopia, when we look at the equatorial region, we may find like different messages. But also there is another element. If the majority of the models, sometimes they agree on a specific message, there is high confidence also on that message. But as Waswa said, the uncertainty is high related to rainfall and to the flows. Thank you very much. The last question, it is also connected to the previous question. If anyone would like to answer that question or would like to provide any kind of feedback, how will water storage of natural lakes and reservoirs affected also by climate change, the water storage and these natural lakes, reservoirs, how they are affected also by climate change? If someone would like to add anything related to this question.
Yeah, I think I still, again, almost similar to the first question, but what we are seeing here that the storage in these reservoirs and lakes also associated with the decreases and increase of precipitation, but also we see continued rise in temperature, and what we may see that there is expected decrease in the water storage, and sometimes maybe these reservoirs and lakes may become drier as time goes on, because there could be that continued variability, evapotranspiration going up, temperatures are rising, the rainfall is unpredictable, and what may happen is that the storage is definitely going to reduce, and eventually we expect them to become more drier. That's my take.
Thank you very much, Waswa. Ethiopia, would you like to add anything maybe related to teleconnections? Because you made an excellent presentation related to teleconnections, and maybe like this sea surface temperature, for example, this Nino 3.4 area in the Pacific Ocean. And we know that the temperature is increasing. If we are expecting like more El Ninos in the future, or maybe less La Ninas in the future, how will that impact these storage or these reservoirs? Thank you. Back to you, Ethiopia.
Okay, thanks, Modathir. Yeah, that is a good question. In terms of SSTs and sea surface pressure anomalies, they oftentimes affect the patterns of precipitation. So it is true that we don't really see a significant increase or a decreasing trend in precipitation. So we've done a lot of analysis in Ethiopia as well to evaluate whether there's a significant trend of increase or decrease, similar to what we see in temperature. So we don't really see that in precipitation, but what we see is changes in these patterns. So in terms of SST anomalies or sea surface pressure anomalies, it usually shifts the beginning of that precipitation period by a couple of days, weeks, or even up to a month, which usually causes drought-induced water scarcity in areas that are highly reliant on rain-fed agriculture. So if that timing or magnitude of precipitation cannot be relied upon, then that usually causes reduction in crop yield or what we call agricultural drought. So that can also be translated into water available in reservoirs and lakes. So when these precipitation patterns are affected, we usually can't operate man-made reservoirs the way that we do normally. And similarly, we may not be able to get the amount of lake level water in lake levels. So it definitely impacts lake level water as well as storage.
Thank you. Thank you very much, our panelists, for this wonderful and fruitful session. And I appreciate very much your participation and also submitting your papers for this important session. I think you shared very valuable and informative information with our Nile Basin stakeholders. Thank you very much, Dr. Kinna. Thank you very much, Ms. Ethiopia. And thank you very much, Mr. Gizaccio and Mr. Waswa. And thank you also for responding very well to the questions of our participants. And also thank you very much for your valuable feedback also during this panel discussion. The final thing I would like to say is now at 2 p.m. we have another interesting session. It is moderated by WMO, and I can give like 1 minute to Washington. If you can advertise your session, the next session, it is at 2 p.m. today. Washington, if you can hear me.
Thank you very much, Dr. Mudathir. Dear participants, thank you very much for attending this wonderful session in the morning. And would like to invite you for our afternoon session, where we'll be talking about the UN early warnings for all. And WMO colleagues, plus some of our experts from GEO and UNDRR, they will be able to also present how they contribute to the UN early warnings for all. So it's my pleasure to invite you all to our afternoon session, just to learn some of the initiatives that WMO is undertaking, especially in the region and globally, that could be of benefit to most users, and addressing some of these challenges like floods, drought, and also the other disasters relating to water. So thank you very much, and meet you all in the afternoon. Thanks, Mudathir.
Thank you very much for this good explanation about the coming session, which, as I said, it will be moderated by WMO at 2 p.m. East African time. Thank you very much again, our panelists, and also our participant in this session, and see you soon in the next session. Thank you and bye-bye. Thank you.
Thank you.